Okay, so let's see more about stability of control systems. So we have the conditions for stability as bounded input, bounded output. So which means for a fixed range of input or a finite range of input, your output should also be finite, and that is your BIBO condition, and the system is stable if it satisfies your BIBO condition or bounded input, bounded output condition. So let's see two examples where your BIBO conditions are both satisfied as well as not satisfied. So in case of example 1, my system is a cos function. So what it does is it applies cos to the input x. So my system output is given by y is equal to cos x. Now let's test for our BIBO condition or bounded input bounded output condition. So my range of x is defined from 0 to pi or 0 to 180 degree, and we all know that cos 0 is 1 and cos 180 is minus 1. So in this case my input is bounded from 0 to 180 and my output is bounded from 1 to minus 1. Hence my system is a stable system. Good. So this is my first example, and next we have example 2 where I'm going to do slight alteration to this system. I'm going to take 1 by cos as my system function. So now my output is given by 1 by cos of x, and let us see for the same set of input between 0 to pi, my system will fail the BIBO test because cos 90 is 0 and 1 by cos 90 is infinity. So this system is unstable for that particular value of 90. But we cannot use this system for any values between 0 to 180 because that particular value is going to render the system unstable and it is not recommended for use. So the next topic for today's class is mathematical model of mechanical elements. So in this we will see how we can use control equations or control system to model your mathematical or mechanical elements. So I'm getting confused with these two words. So the mechanical systems can be modeled mathematically using first order and second order differential equations. So the first order and second order differential equations are linear and are LTI. So we are using them because they satisfy this LTI condition of ours. So my first order differential equation is d by dx and my second order differential equation is given by d square by dx square. And now what I am going to do is I am going to write the mechanical elements using these differential equations. So let's see how we do those. So now we will see what is a mechanical building blocks that we are going to represent using our control differential equations. So we have three blocks or the three building blocks for a mechanical system, namely mass, spring and a dashpot. So your mass is responsible for the force equal to mass into acceleration. Your spring is responsible for the extension and your dashpot is responsible for the suspension. Good. It acts as a shock absorption, you can say. So now let us see what is the differential representation for this mechanical building blocks. So for force, we are having m into d square x by dt square, so which is the acceleration, right? Because if x is my displacement, my dx by dt is your velocity, and d square x by dt square is your acceleration. Now for spring, I'm going to use the variable k to represent my spring equivalent, and it is given by k into x, and for dashpot the scalar variable is b, and it is represented by b into dx by dt. Good. Now these three are the building blocks which are used to model your mechanical system, and these three building blocks have the force equivalent representation given by m into d square x by dt square, F is equal to kx, and F is equal to b dx by dt. Now this relativity, so we are going to say relative in position, meaning whenever you have a spring and a dashboard and they have two ends and they are both connected to different masses, you may have that they are connected to different masses, and you have displacement x1 which is related to a mass m1, and you have a displacement x2 which is related to mass m2. In that case we need to take the relative displacement, so which means I am having k into x1 minus x2 b into d by dt of x1 minus x2. So we are going to see more on this relative positioning in this numerical example. So here I have a much complex mechanical system which is still built using only those three building blocks. So I am having masses m1, m2, m3. Then I am having my springs K1, K2, K3. Then I am having my dashpots B1 and B2. Now the displacement of mass M1 is given by X1. The displacement of mass M2 is given by X2. And the displacement of mass M3 is given by X3. Now the question is, obtain the force equivalent representation for masses m1, m2 and m3. Or in general, the question can be, give the force representation of the following mechanical systems. So what are the steps that we need to follow to solve this numerical? So the first step is isolate your masses m1, m2 and m3. So take them separate and compute them separate. Then write the force equation for your masses m1, m2 and m3. Good. So the integrate, so I don't think that is not needed right now. So we'll just stick to this A and B for now, and when we see more complex numericals or more advanced numericals, we will see the third step. So for now we are good with A and B. So as a first step, what I'm going to do is I have isolated my mass m1, and now I need to write what are the forces that are acting on my mass m1. So always the Fm1 is due to the mass m1 on itself. So that is force due to mass m1, and the other things are, there is a k1, v1 and k2 acting on it, and then there is this f of t. There is a force which is given by f of t. Now what I'm going to do is I'm going to write my net equation. So before that, let us see what are, if there is any relative positioning. So we will see. I'm just writing the full form, and what are the things that are acting on m1. Good. So now m1 is your isolate mass. So next we will look for relative displacement. So if I see on m1, I can tell from looking that k2 is connected to both mass m1 and m2. So mass M1 is undergoing displacement x1, whereas mass M2 is undergoing a displacement of x2. So the force K2 becomes relative because of the displacement x1 and x2. So I am going to write just Fk2 in this slide, and that is given by K2 into x1 minus x2. Here the next thing, the third thing you need to know is the order of the displacements in your relative displacement equation. So the first displacement is always the displacement of the isolated mass in question. So in this case, my isolated mass is m1, which means my first displacement in the relative equation is going to be x1. And if this is the case for any isolated mass, we are always taking the displacement with respect to the isolated mass for which it is calculated. So we will see that for M2 as well as M3. So it will be clear when we see this relative representation for masses M2 and M3. And the next thing you need to be, you need to get it understood in this kind of numerical, the direction of the force is not at all important. So here the force equation for mass M1 is given as the total force F of t is equal to Fm1 plus Fk1 plus Fb1 plus Fk2. So all the other forces combined is equal to the net force F of t. And here if you see the direction of the force, you don't need to think in which direction the force is acting and in which direction the mass M1 is getting pulled into. You don't need to worry about all those. You just write all the forces with sum. So your all forces get summed in these kind of models. And now I'm writing the differential form in terms of displacement for Fm1, Fk1, Fk2 and Fd1. Good. Here again I am telling you the first displacement is always the displacement of the mass in isolation, and now I can write my force equation for mass M1 in terms of these differential representation as so on. So now this is my force representation for mass M1. Next, we are going to isolate your mass M2 and do the same steps which we followed for M1. So I am isolating mass M2, and what are the forces that I on M2? So I have my Fm2, then I have my Fk2, then on the other side I have my Fk3, then I have my Fb2. F of t doesn't influence M2 because F of t is connected only to M1 and it is left hanging and not separated from M2. So now we are going to check three things for this isolated mass M2. The first one being the relative displacement, the second one being the force with positive, and the third being the displacement order. So the force equivalent equation is given by the net force, in this case is 0 because there is no F of t. So Fm2 plus Fk2 plus Fk3 plus Fb2. So all the forces are summed together, and the net force acting is the sum of all the forces, and that is equal to 0. Good. Probably it comes from some theory of mechanical physics, maybe. So, but I will just say that the sum of all the forces is equal to 0. And here the relative displacements happens for Fk3, which is connected between M2 and M3, Fb2 also connected between M2 and M3, and Fk2 is connected between M2 and M1. So the relative displacement for Fk3 is what? Yes, x2 minus x3. The same for B2, and for Fk2 it is x2 minus x1. So if you see here, your first displacement is the displacement of the mass in question, that is your M2. So in this case, all the relative displacements start with x2 because it is always going to be x2 as per our assumption, right? So isolated mass here is M2 whose displacement is x2. So the rule that we are following is the relative displacement's first displacement is going to be that of the isolated mass. So now I can write the force equations in differential form. Then I can write the net force equation also. So one thing I like to point out in this is that your mass is never relative. Mass is always isolated. So that is like the opposite of relative. So that is why we call it as an isolated mass, and M2 is never going to be relative. So don't mistake and do relative displacement for the masses. So now I can write my force equivalent equation as Fm2 plus Fk2 plus Fk3 plus Fd3 equal to 0. This is the force equivalent equation for our mass M2. Good. So I think you're getting the hang of it. So now let us see how this works for mass M3. So the same procedure we are going to follow, and for mass M3 you have what are the forces acting on M3? Definitely Fm3, Fk3 and Fb2. Good. These are the three. On the other side it's left open, so there is no forces acting on the other side of M3. And now let us check for again these three conditions. We will do first relativity. The force equivalent, which is the sum of all forces, equal to 0, and the third condition is the order of your. So now let us see what is the force equivalent equation here. So the force equivalent equation is Fm3 plus Fk3 plus Fb2 equal to 0, and your relative displacement for K3 and B2 is gonna be x3 minus x2. So x3 comes first because the isolated mass M3's displacement is x3, and that comes first. So now let's write the differential form for Fm3, Fk3 and Fb2, and your force equivalent equation is gonna be the sum of these three. Good. So that is this numerical. So that is how you solve these numericals for the force equivalent or the force representation for masses M1, M2 and M3. Thank you.